All right. Welcome to the deep dive. We're kicking off our GCSE Computer Science series and, diving into algorithms.
Ooh, algorithms. Sounds a bit scary, but
Yeah, it does sound a little complicated, but honestly, it's simpler than you think.
yeah, much simpler.
So an algorithm, it's basically just like a set of instructions. It's
Hmm.
a step-by-step guide
Hmm.
to solve a problem.
Yeah, like a recipe.
Exactly like a recipe. And it's the fundamental building block for like everything your computer does.
Absolutely everything.
Even like watching YouTube or playing video games, it's all thanks to algorithms.
Yeah. And if you're in year 9, 10, or 11, getting ready for those computer science GCSEs,
Oh, yeah, those exams.
understanding algorithms is essential.
Totally. And that's why we're doing this whole series. We're going to break it all down, make it easy to understand.
Yeah.
In this deep dive, we'll be focusing on the basics. What algorithms are, how we can describe them, and some key examples that you need to know for your exams.
Right. So let's get started with the basics then.
Okay, so when we talk about actually creating algorithms, it all comes down to this thing called computational thinking.
Yeah, computational thinking.
It's got like three main principles.
Okay.
The first one is algorithmic thinking, and that's the one we're focusing on today.
So algorithmic thinking is basically about coming up with those step-by-step instructions to solve a problem.
Exactly. But there are also two other super helpful principles called decomposition and abstraction.
Yeah, these are really important when you're tackling bigger problems.
Yeah, for sure. So decomposition is like taking a huge, complicated problem and breaking it down into smaller, more manageable chunks.
It's like when you have a really big project to do, you wouldn't try to do it all at once.
Right.
You'd split it up into smaller tasks.
Yeah, like if you were planning the school fit, you wouldn't try to plan everything at once.
Exactly. You'd break it down into setting up stalls, organizing games, sorting out the food and drinks, all those things.
Yeah, and then each of those smaller tasks is much easier to deal with.
Right.
Okay, and then we've got abstraction.
Okay, so abstraction is all about focusing on the important stuff
Yeah, just the essentials.
and ignoring all the unnecessary details.
Yeah, like when you're using a bus route map.
Oh, yeah, good example.
It shows you the bus stops and the routes,
Yeah.
which is all you really need to know to get from A to B.
Yeah.
It doesn't show you like every single building or tree the bus passes. That would just be too much information.
Way too much. And it's not relevant to what you're trying to do.
Right, so algorithmic thinking, it uses both decomposition and abstraction to come up with the steps to solve a problem.
Absolutely.
So we've got a pretty good idea of what algorithms are now,
Yeah.
but how do we actually represent them? Well, like how do we write them down or draw them out so we can understand them and eventually tell the computer what to do?
Yeah, good question.
We've got two main tools for this: pseudocode and flowcharts.
Okay, let's start with pseudocode. What is pseudocode?
So pseudocode, it's kind of like a mix between plain English and actual computer code.
Right. A bit of both.
It's a way of describing an algorithm using short, clear phrases that are structured in a logical way.
So it's not as strict as a real programming language,
Exactly. It's more flexible and easier to understand.
but it still has some structure so you can clearly see the steps involved.
Yeah, and for your GCSEs, you'll probably be using something called the AQA standard style of pseudocode.
Right, the AQA standard.
This uses specific keywords to represent common actions, like output, input, if, else, for, and while.
It's really important to get familiar with these keywords.
Definitely.
Okay, so that's pseudocode. What about flowcharts?
Flowcharts are more visual.
Ah, so instead of text, they use different shapes to represent different parts of the algorithm.
Yeah, so you might have a rectangle for a process or a calculation,
And a diamond for a decision point where the algorithm has to choose between two different paths.
and then parallelograms for input and output where data comes in and goes out.
Element. Arrows connect all these shapes to show the flow of the algorithm, the order in which things happen.
Right, so to sum it up, pseudocode is text-based, quite structured, but still easy to read, and flowcharts give you a visual overview of the algorithm.
Yeah, they both have their advantages.
Both are super useful for planning out your algorithm before you start writing any actual code.
Absolutely.
Okay, so
Um,
let's say you're faced with a problem and you want to solve it using an algorithm.
Right.
It's important to have a systematic approach.
Okay, systematic approach. What does that mean?
It means thinking logically, breaking the problem down,
Yeah.
remembering those principles of decomposition and abstraction,
Yeah.
and then using our algorithmic thinking to come up with a clear step-by-step solution.
A good example of this is searching for something in a list.
Oh yeah, like imagine you have a list of usernames and passwords,
Right.
and someone enters their username. The algorithm would need to find that username in the list and then check if the password matches.
Yeah, that's a very common task for computers.
And it needs a systematic approach to make sure it checks everything properly.
We could even write a bit of pseudocode for this. You would have input to get the username from the user. Then you'd use a loop, maybe a for loop, to go through each username in the list.
Okay.
Inside the loop, you'd have an if statement to check if the current username matches the one entered by the user.
And if it does?
Then you check the password, and if that matches too well, then you found the right user.
Great. So we've talked about how algorithms take an input, do something with it, which is the process, and then produce an output.
Yeah, those are the 3 key stages.
Let's explore those a bit more.
Okay, so input, that's any kind of data that we feed into the algorithm.
It could be something typed in by a user, a click on a mouse data from a sensor, or information stored in a file.
Yeah, anything, really.
Then you have the process, which is what the algorithm actually does with that input, the calculations, the decisions, the actions it takes.
Right.
And finally, the output is the result, the answer, the thing the algorithm produces.
Yeah, it could be something displayed on the screen, an image, a sound, or even a physical action like a robot moving.
So many possibilities.
Hello?
Okay, let's do a simple example. What would be the input, process, and output for an algorithm that calculates the area of a rectangle?
Okay, so for that, the inputs would be the length and width of the rectangle.
Right, makes sense.
The process would be multiplying those 2 values together.
Simple multiplication.
And the output would be the calculated area.
Easy peasy.
How about another one? Let's say we want to calculate the average test score for a class.
Ooh, okay. What would the input, process, and output be for that?
Okay, so the input would be the number of students in the class and then each student's individual test score.
Okay.
The process would involve adding up all the test scores to get the total and then dividing that total by the number of students.
So 2 steps in the process this time?
Yeah.
And the output.
The output would be the average test score.
All right, here's a trickier one.
Yeah.
Imagine a bus company offers a discount if you have a student card or if you're over 65.
Oh, okay. I like this one.
If we were designing an algorithm to decide who gets the discount, what would the inputs be?
Let me think. So we need to know if they have a student card, so that would be a yes or no input.
Okay.
And we also need to know their age.
Right, so 2 inputs. Again, this time it's student card status and age.
Exactly. And then the algorithm would use those inputs and the bus company's rules to figure out if they get the discount.
Awesome. So we've got our algorithm, we know how to represent it, and we understand inputs, processes, and outputs.
Yeah, we're making good progress.
But how do we know if our algorithm actually works correctly before we turn it into a real program?
That's where we use tracing and trace tables.
Okay, what are those?
A trace table is a way of testing your algorithm on paper before you write any code.
So it's like a manual test run.
Exactly. You step through the algorithm line by line, just like a computer would, and you record what happens to the variables and the output at each step.
We've got an example here of an algorithm that finds the highest of 10 numbers entered by a user.
Oh, yeah, I see it.
The trace table for this algorithm has columns for the count, the highest number, and the output.
Right, let's walk through it.
Okay, so the algorithm starts by asking the user to enter 10 numbers.
Okay.
The first number they enter, let's say it's 4, that automatically becomes the highest number because it's the only one we have so far.
Right.
So in our trace table, the count is 1. The highest number is 4, and there's no output yet.
Okay.
Then the user enters the second number. Let's say it's 3.
Okay.
Now, the algorithm compares 3 to the current highest number, which is 4.
Right.
Is 3 higher than 4?
Nope.
So the highest number of the trace table stays as 4.
Makes sense.
The count increases to 2 because we've now had 2 inputs.
Okay.
And there's still no output.
Got it.
Now let's say the user enters 7 as the third number.
Okay.
The algorithm compares 7 to the current highest number, which is still 4.
Okay.
Is 7 higher than 4?
Yes, definitely.
So in the trace table, we update the highest number to 7.
Right.
The count becomes 3, and still no output yet.
Okay, I'm starting to get the hang of this.
Yeah, it's pretty straightforward.
Yeah.
And this process continues for all 10 numbers that the user enters.
You keep comparing each new number to the current highest number and updating the trace table accordingly.
Exactly. And by the end, the trace table will show you the final highest number, which in our example with the numbers 4, 3, 7, 1, 8, 3, 6, 9, 12, and 10.
Oh, wow, that's a lot of numbers.
I know, right? But the highest number would be 12.
Of course.
We also have another example with just 2 variables, x and y, and a while loop.
Right, a while loop is a section of code that repeats as long as a certain condition is true.
Exactly. And even with just a few lines of code, the trace table helps you visualize how those variables change with each repetition of the loop.
It's a really good way to catch any mistakes in your logic.
Yeah, it's much better than just staring at the code and trying to figure it out in your head.
Absolutely.
Okay, so once we have an algorithm that works, we we might start thinking about how good it is.
Yeah, how efficient it is.
Exactly. And in computer science, one way we measure that is through algorithm efficiency.
Right. So what do we mean by efficiency in this context?
Well, it's basically about how well an algorithm uses resources like time and memory to get the job done.
Ah, so a more efficient algorithm will use less time and less memory.
Exactly. And for the same problem, you might have different algorithms that can solve it, but some will be much faster or use less memory than others.
Right. Especially when you're dealing with a lot of data.
We mentioned searching algorithms earlier, right?
Yeah. Linear search and binary search.
Both of those can find a specific value in a list, but
Mhm.
depending on how big the list is and whether it's sorted or not, one might be way faster than the other.
Okay, that makes sense.
And it's not just about searching. Let's say you want to sort a list of numbers in ascending order.
Right.
We have two sorting algorithms here, bubble sort and insertion sort.
Okay, I've heard of bubble sort.
Yeah, it's a classic.
Yeah.
So if you have a list of 20 numbers all jumbled up, both bubble sort and insertion sort, you can put them in order from smallest to largest.
Yeah, but which one is more efficient?
Well, in the worst case scenario, bubble sort might need to do about 361 comparisons.
Wow, that's a lot.
I know, right? Whereas insertion sort might only need about 190 comparisons.
Okay, so insertion sort is more efficient then.
Exactly. Even though both algorithms achieve the same result, insertion sort does it with fewer operations.
So it would probably be faster.
Yeah, especially if you have a really long list of numbers to sort.
Right, that makes sense. So understanding algorithm efficiency helps us choose the best algorithm for the task.
Absolutely. Okay, so let's dive into those searching algorithms we mentioned earlier, starting with linear search.
All right, linear search.
How does that work?
Linear search is the simplest way to search for something in a data set, like a list.
Okay.
You start at the beginning and check each item one by one until you find what you're looking for or you reach the end of the list.
So it's like looking for a specific song in a playlist by just scrolling through from the top.
Yeah, exactly. That's a good analogy.
And it doesn't matter if the list is sorted or not.
That's right. It works either way.
So the steps are you look at the first item. If it's the one you want, you're done. If it's not, you move on to the next item and keep repeating until you find it or you've checked everything.
And we have a Python code example here to show how you might implement a linear search.
Cool.
It basically uses a loop to go through each element in the list and checks if it matches the target value.
Okay. Makes sense. What about binary search? How's that different?
Binary search is much more efficient,
Ooh, efficient.
but there's a catch. It only works if the data is already sorted.
Ah, okay. So you need to sort the data first.
Yeah.
So how does it actually work?
Well, you start by looking at the middle item in the sorted list.
Okay, the middle item.
If that's the value you're looking for, you're done.
Easy.
But if your target value is smaller than the middle item,
Smaller.
then you know it must be in the left half of the list.
Ah, because it's sorted.
Exactly. So you discard the right half and only search in the left half.
Makes sense.
And if your target value is larger than the middle item...
Then you search the right half.
Exactly. You keep doing this, having the search area until you find the value or you run out of places to look.
Wow. So it's like narrowing down the possibilities with each step.
Yes. It's very similar to how you'd look up a word in a dictionary.
Oh, yeah. You wouldn't start from the beginning and read every word.
No, you'd open it somewhere in the middle and see if your word comes before or after that page.
Right. And then you'd adjust accordingly.
That's exactly what binary search does. And it works for both numbers and words.
So when would you choose linear search? And when would you choose binary search?
Good question.
What are the pros and cons?
Linear search works on unsorted data.
Okay, that's a big plus.
And it's usually faster for very small data sets because binary search has some extra steps involved.
Right.
Plus, linear search is really simple to understand and to write the code for.
Okay.
But the downside is that it can be very slow for large data sets because in the worst case, you might have to check every single item.
Yeah, that would take ages.
And it's not very efficient if you need to search the same data set multiple times.
Okay, what about binary search then?
Binary search is super fast for large data sets as long as they're sorted.
So that's the trade-off. It needs sorted data, but it's much faster.
Yeah. And it's also very efficient for repeated searches on the same data set because you only need to sort it once.
Right.
But of course, the biggest downside is that the data must be sorted first, and sorting itself takes time and resources.
Okay, I'm getting a good grasp of these searching algorithms now.
Day two.
Let's move on to sorting algorithms then.
Right, sorting algorithms.
These are the algorithms we use to arrange data in a specific order, like putting numbers in order or arranging words alphabetically.
Yeah, very useful algorithms.
We're going to look at two common ones, merge sort and bubble sort.
Okay, I'm intrigued.
Let's start with merge sort.
So merge sort, how does that one work?
Merge sort uses a clever technique called divide and conquer.
Divide and conquer sounds interesting.
It is. It basically means you break the list down into smaller and smaller sublists until each sublist has only one element. And a list with one element is already sorted by definition.
Okay.
Then you start merging these sublists back together in the correct order until you end up with one fully sorted list.
So you divide it all up and then merge it back together in the right order.
Exactly.
Yeah.
We have a Python code example here that shows how it's done.
Okay.
The key part is the merging process. When you have two sorted sublists, the algorithm compares the first elements of each sublist and picks the smaller one to go first in the new merged list.
Okay.
And it keeps doing that, comparing and picking the smaller element until all the elements from both sublists are in the new merged list.
Right, so you're constantly comparing and merging until you have the final sorted list.
Exactly.
What about bubble sort?
Bubble sort. It's a classic. It's called bubble sort because the larger elements bubble up to their correct position with each pass through the data.
Okay, I like that name.
So it works by repeatedly going through the list, comparing pairs of adjacent elements and swapping them if they're in the wrong order.
So if you're sorting numbers in ascending order and you find two numbers where the first one is bigger, you swap them?
You got it. And you keep doing these comparisons and swaps until the whole list is sorted.
Right.
We have an example here with the numbers 5, 2, 4, 1, 6, and 3.
Okay.
And you can see how with each pass through the list, the larger numbers gradually move towards their correct positions.
Yeah, like bubbles rising to the top.
Exactly.
Yeah.
We also have an example with sorting words alphabetically, like milk, eggs, bananas, cheese, potatoes, and grapes.
Okay.
And there's also a Python code example for bubble sort.
So bubble sort is all about making these passes through the data, comparing and swapping until everything is in the right order.
Exactly. It's a simple concept, but it can be a bit slow for large data sets.
So when would you choose merge sort versus bubble sort?
That's a good question.
What are their strengths and weaknesses?
Merge sort is generally more efficient, especially for large data sets. And it works well even if the data is initially very messy. But it can use more memory than bubble sort because of those temporary sublists it creates. And it's a bit more complex to understand and implement.
Okay, what about bubble sort then?
Bubble sort is super simple to understand and decode, which makes it great for learning the basics of sorting.
Yeah.
But it can be very slow for large data sets because it often needs to do many passes through the data.
So it's simple, but not always the most efficient.
Exactly. You wouldn't want to use it for sorting millions of items.
No, probably not.
Well, that was quite a deep dive into algorithms.
Yeah, we covered a lot.
We learned that algorithms are basically step-by-step instructions that drive everything a computer does.
They're the foundation of computer science.
And we saw how they can be represented using pseudocode and flowcharts.
And we talked about the importance of having a systematic approach to solving problems.
And those key stages, input, process, and output.
We even learned how to test algorithms manually using trace tables.
And we got an introduction to algorithm efficiency, comparing linear search and binary search.
And we explored two sorting algorithms, bubble sort and merge sort.
That's a lot for one episode, but it's all really important stuff for your GCSEs.
Absolutely.
So here's a question to think about. Now that you know how algorithms work,
Okay, I'm listening.
can you identify any everyday tasks that are basically algorithms?
Like what?
Like making a cup of tea,
Oh, yeah.
or following instructions to assemble something.
Right.
Try breaking those down into step-by-step instructions and see if you can spot the algorithm.
That's a fun challenge.
And here's another one to ponder. Think about those searching and sorting algorithms we discussed.
Okay.
Can you imagine situations where one would be much better than the other?
That's a good one to think about.
It all depends on the data, the size, whether it's sorted, and how often you need to search or sort it.
Yeah, that makes sense.
That's all for our first deep dive into algorithms.
Thanks for joining us.
Join us next time for more GCSE Computer Science fun.
See you then. Bye.